We continue our discussion of quantum physics, and in this section, we will look at different energies that photons have and what constitutes the electromagnetic spectrum. So far, we have learned that the reason how or why quantum physics came about as a break from classical physics was that classical physics was unable to explain the exact shape of the black body radiation. So in order to explain that, Max Planck came up with the idea of quantization. So he basically proposed that atoms and molecules oscillate at certain discrete frequencies, and these frequencies were uh, associated with the energy of these atoms and molecules. So the energy of these atoms and molecules are discrete. They're multiples of what's called Planck's constant and frequency. So not only do these atoms and molecules oscillate at discrete frequencies, but they can also absorb energy at those discrete energies, and they can also emit discrete energies. So none of this is continuous. You can either absorb or emit 2 joules of energy or 3 joules, but nothing in between. So that those numbers are just an example of for what discrete energy means. The next uh, idea or the next observation which strengthened the foundation of quantum physics was photoelectric effect, whereby it was observed that in order to explain photoelectric effect, light had to be treated as made up of particles rather than waves. And these particles of light are called photons. And photon also has energy associated with it, and that's equal to Planck's constant times the frequency. So that's shown here in this equation, E equals HF. You can write this energy in terms of frequency like this, or in terms of wavelength, using the relationship frequency is speed divided by wavelength. Here, c is the speed of light, because that's what we are talking about. I gave the value of Planck constant can either be expressed in joules seconds or electron volt seconds. In electron volt seconds, the value of Planck's constant is 4.14 times 10 to the negative 15. The constant Hc that appears in this equation here has a value of 1240 when it's expressed in the units electron volts nanometers. And the reason why this is a useful quantity to know is because often energy at the atomic scale are expressed in electron volts, and wavelengths of electromagnetic radiation is expressed in nanometers. So let's look at the different possible frequencies that electromagnetic radiation can have, and that's shown in this diagram. So as you go from left to right, the wavelength is decreasing, and the frequency shown here at the bottom is increasing. So the frequency goes from 1 hertz on this end to 10 raised to 24 hertz on that end. And electromagnetic waves of different frequencies or wavelengths are given certain names. The lowest frequency wavelengths are called radio waves, and then within that we have microwaves. Also within radio waves are waves at or frequencies at which AM radio signals are transmitted, or FM radio and television signals are transmitted. Now, if you go to larger frequencies, you get to what's called infrared. And then beyond that, you get visible light, which, as you can see, is a very small sliver of all possible wavelengths of electromagnetic radiation. So only this portion of the electromagnetic radiation is visible to us. Our eyes are sensitive to only these frequencies. And then as you go to higher frequencies, you get ultraviolet rays and then X-rays. And then the highest frequency is gamma rays. So this is the electromagnetic spectrum and different parts of it. Now, since energy is directly proportional to the frequency, high frequency on that spectrum corresponds to high energy. So gamma rays are the highest energy photons, and radio waves are the lowest energy. One outcome of gamma rays being highest energy or having very high energy is that they can easily ionize atoms. So if gamma rays collide with atoms, they can strike electrons out of the atom, meaning they can ionize them. Other smaller energy radiation is also able to ionize, not to the same extent, but to some extent. And so X-rays and ultraviolet rays are also able to ionize atoms. So these radiations can ionize molecules in biological tissues. They can kill cells or damage their ability to reproduce, and that's what causes cancer. And interestingly, ionizing radiation can also be used in treating cancer by damaging cancer cells. So if you can focus on the bad cells, you're able to damage them and stop the spread of cancer. The energy of gamma rays and X-rays are such that they can penetrate materials like skin and tissue. And that property is useful in creating images of the inside of objects, including bodies. So that's why gamma rays and X-rays are good diagnostic tools in the medical field. So what are X-rays? How are they produced? They're produced when high-speed electrons are brought to rest abruptly when they strike a metal target. So you have high-speed electrons colliding with a metal target, and when they do so, they're suddenly brought to rest. And since they were going at high speeds, and if you bring it to sudden rest, then you're creating a large deceleration. And whenever you have an acceleration of a charged particle, that results in emission of electromagnetic radiation. So same thing in this case. It results in production of radiation, which is called braking radiation because they're coming to an abrupt stop. The original term from German is Bremsstrahlung. Bremsstrahlung basically means braking. Literally, it means braking radiation. Let's look at the basic setup for producing X-rays. So you have a metal target at the top here. And then on this end at the bottom, you have a heated element which emits electrons. And you have to maintain a high potential difference between the top and the bottom in order to be able to accelerate the electrons in the upward direction. This glass bulb that you see here is basically vacuum inside. You don't want electrons to slow down by hitting other molecules in there. So you don't want anything else in there. So it's a vacuum tube, and electrons are accelerated upward, and then they are brought to rest when they hit the metal target. In that process, electromagnetic radiation is emitted, and that's shown here. Depending on the energy of the incident electrons, that will determine the energy of the radiation and therefore its frequency. So you can have different possible frequencies, and that's shown in what's called the X-ray spectrum. This is the X-ray spectrum. On the y-axis, you have X-ray, the intensity of X-rays, and as a function of frequency. So you see that most of the spectrum is just a smooth curve. And that is X-ray being produced because the electrons are coming to an abrupt stop. And depending on the initial velocity of the electrons, you will have X-ray of different frequencies being produced. Electrons will have a maximum kinetic energy, which depends on the potential difference you're applying across the X-ray tube. And that corresponds to the most energetic photons or X-rays corresponding to the maximum frequency you will see here. And that's shown by this point here in the graph. What is the maximum kinetic energy you can have is if Q is the charge of the electrons and V is the potential difference across the X-ray tube, then QV is the energy that these electrons will acquire as they traverse along the length of the tube. So if the potential difference here is V, charge of the electrons is Q, then as they are accelerated from the bottom here to the top here, the energy they will acquire in that process is QV, and that's what's going to give you the highest energy photons, whose energy would be HF max. So in addition to the smooth part of the curve, we also notice these spikes. So the smooth part of the curve is the Bremsstrahlung electrons being brought to rest. The spikes that you see here, two of them in this graph, those are called characteristic X-rays. Characteristic X-rays. And the reason why they are called characteristic X-rays because their location is the signature of the material of the target. Different elements, different metals will have spikes of different shapes in different locations. And the reason why you get these spikes, why these spikes are produced, because if the energy of the incoming electrons correspond to the what are called different energy levels inside the atom of the metal, then these electrons can be absorbed, and they can be absorbed, and the atom then has a higher energy than it did before. But that only lasts for a small period of time, and then eventually the atom falls back to the original energy it had. And when it falls back, the excess energy is released, is emitted in the form of characteristic X-rays. And the reason why the location of these X-rays is a signature of the material of the target is because different atoms have different energy levels. So they can absorb and emit photons of different energies. They're not going to be the same. So by looking at these spikes, one is able to identify the material, what metal that target is. And that's one of the ways of identifying presence of certain elements in an alloy. Okay, so beyond X-rays, we get to ultraviolet rays, and these are given off by hot solids or gas when they absorb and then re-emit energy. They have similar biological effects as gamma and X-rays, but milder. And that's why if you are in the sun for long, it's best to use sunblock, because sunlight has a good amount of ultraviolet radiation, and that can be dangerous for the skin. In addition to being dangerous, ultraviolet rays also trigger production of vitamin D in the skin, so there is some benefit as well. Visible light cannot help the body produce vitamin D, but only ultraviolet rays can. Okay, let's look at problem number 29. So in this problem, what is the accelerating voltage of an X-ray tube that produces X-rays with the shortest wavelength of 0.0103 nanometer? Shortest wavelength corresponds to largest frequency. So basically, we're looking for the equation for maximum frequency. So we have to figure out V, and we are given that lambda minimum value of lambda is 0.0103 nanometers. The equation for the energy of maximum frequency photons or maximum frequency radiation is EV equals HF max. Here we are working with wavelength instead of frequency, so we're going to write it using wavelength rather than frequency. So frequency is speed of the wave, in this case, speed of light, divided by lambda min. So if you solve this equation for V by dividing both sides by E, you get this equation. V equals hc over lambda min E. E is the charge of the electron in this case. And then you plug in the numbers. The Planck constant value that's inserted here is in joules seconds to keep everything in SI units. And then speed of light, wavelength, and then charge of the electron. So it comes out to 221 kilovolts. And then you can convert it to electron volts by using the conversion factor, or you can directly use that number 1240 that we saw earlier. That's the value of Hc, 1240 electron volts nanometer. So if you use that directly, all you have to do is, so Hc is 1240, and lambda min, you can leave it in nanometers. So all you have to do is divide 1240 by 0.0103, and that will give you the equivalent potential difference in electron volts. Let's look at Problem number 26. In this problem, calculate the energy in electron volts of an infrared photon of frequency 2 times 10 raised to 13 hertz. How many of these photons would need to be absorbed simultaneously by a tightly bound molecule to break it apart? And then in part C, what is the energy in electron volts of a gamma ray of frequency 3 times 10 raised to 20 hertz? And then how many tightly bound molecules could a single such gamma ray break apart? So we're comparing the effect of infrared photons versus gamma ray photons. So for the infrared, we are given that the frequency is 2 times 10 raised to 13, and you can calculate the energy using E equals hf. Since you have to calculate the energy in electron volts, we can use the value of Planck's constant in electron volts seconds, so 4.14 times 10 to the negative 15. And then that's the frequency, which gives us the energy as 8.28 times 10 to the negative 2 electron volts. So this is the problem we're talking about. Okay, in part B, how many of these photons would need to be absorbed simultaneously by a tightly bound molecule to break it apart? So if you look at table 29.1 in the book, that gives you the different values that you need. Let me see. This is the table, and it gives you representative energies for submicroscopic effects. So rotational energy of molecules is 10 to the negative 5 electron volts. Vibrational energies of molecules is 0.1, etc. So in this case, we need binding energy of a tightly bound molecule, because that's what the problem says. The binding energy of a tightly bound molecule is 10 electron volts. So that's what we will use. Let me get back to the problem. So in part B, we have to find how many of these photons would need to be absorbed simultaneously by a tightly bound molecule to break it apart. So basically, the amount of energy you need is the energy with which these molecules are held together. So you're looking for an energy of 10 electron volts, and what you have is 8.28 times 10 to the negative 2 electron volts per photon. So the question is, how many photons are we going to need? So you just divide 10 by the energy of each photon. So you will need 121 photons to break that molecule. And then we move on to gamma ray, which has a much higher frequency, 3 times 10 raised to 20. So that's our frequency. And we basically go through the same steps as in the previous parts. And we find that the energy of each photon is 12.52 times 10 raised to 5 electron volts. And then when you divide that by 10, that gives you the number of molecules that a single gamma ray can, a photon can break apart. So the question is different in parts B and D. In part B, we were asked how many photons are you going to need to break apart a molecule. In the next one, how many molecules can the single photon of gamma ray can break. So that's why you notice how the ratio is set up differently. Here it was 10 divided by the energy, and here is the energy divided by 10. So anyway, so one single photon of gamma radiation can break apart, has enough energy to break apart 12.52 times 10 raised to 4 of these molecules. So after ultraviolet, we get to the visible portion of the electromagnetic spectrum. The photon corresponding to the red color has an energy of 1.63 electron volts. Violet has energy of 3.26 electron volts. A single photon from the visible portion can stimulate the retina by triggering a nerve impulse. And then photons can be absorbed or emitted by atoms that have exactly the correct energy steps to do so. And we will talk about these energy steps in more detail in the next chapter, but the idea is each atom of different kind has certain energy levels, and these are discrete energy levels. So energy can, and just to give you an example, an atom can either be in a 1 joule energy state or a 2 joules, but nothing in between. So if the difference between two energy states in an atom corresponds or equals exactly the energy of an incoming photon, then this atom will absorb that photon and go up in energy. It becomes a higher energy atom. And then, as I was saying earlier, it doesn't stay in the higher energy state for long. It falls back to the earlier original energy. And when it does that, the extra energy it had is now released in the form of photons. So for a photon of frequency f to be absorbed, the atom must have an energy difference of hf between two of its energy levels. Then and only then can this photon be absorbed. Because an atom is not going to take an energy of 0.5 HF or 3/2 HF. It will only accept multiple number of HF energies. You have to absorb either one photon or two photon, but not 2.5, nothing in between. So what provides color to different objects that we see? So for example, a violet flower absorbs the red color and reflects the violet. So if you recall the order of the visible spectrum, violet is the highest frequency, red is the lowest frequency. And so a violet flower will absorb all the reds and it will reflect all the violets. So that's why it appears to be violet. And what that suggests is that that material of that flower has energy steps which correspond to red photon energy, but not violet energy photons. That's why it absorbs red and not violet. Materials that are transparent do not absorb any visible light because none of their energy steps correspond to any of these photon energies. So all of the wavelengths, all of the frequencies simply pass through a transparent material without being absorbed. Let's look at problem number 30. What is the ratio of power outputs by two microwave ovens having frequencies of 950 and 2560 megahertz? If they emit the same number of photons per second, what is the ratio of photons per second if they'll have the same power output? So in the first case, the number of photons is the same. And in the second case, the power output is the same. So first we have to calculate the power output and then the number of photons. So power, you will recall from mechanics, from first semester physics, is the rate at which energy is absorbed. So P is E over T. And the energy, we're talking about photons here, so the energy of each photon is Planck's constant times frequency, and if you have n photons, then n times hf1. In the first part, you're emitting the same number of photons, so we use the same n in the numerator and the denominator. So it's basically nhf1 over nhf2. The n and the h cancel out, leaving us with just the ratio of the frequencies. So 950 over 2560. So it comes to 0.371. So that's the ratio of the power output of these two microwave ovens. The one operating at the lower frequency, 950 megahertz, is a little more than a third of the 2560 megahertz microwave oven. In part B, we have to find the ratio of photons per second if they have the same power. So now the power is the same. We're going to equate NHF1 over T. So power is E over T, and energy is NHF divided by T, and then NHF divided by T. We're talking about per second, so T is 1 on both sides. So essentially, and then we can cancel out the H on both sides. So N1F1 equals N2F2. So N1 over N2 is F2 over F1. So 2560 over 950, and that comes to 2.69. So that's the ratio of photons per second if they have the same power output. Then we get to the low energy part of the electromagnetic spectrum. As you cross the visible portion beyond red, you get to infrared radiation. And this has so small of energy that it can't have much effect on atoms and molecules. Water molecules have several states which are separated by 10 to the negative 15 to 10 to the negative 2 electron volts, and can therefore absorb infrared radiation. Microwaves have frequencies corresponding to an energy of about 10 to the negative 5 electron volts, and they can be absorbed by water molecules. And this is what makes microwave cooking or heating possible. So microwaves can absorb or can be absorbed by water molecules, and that raises the energy of the water molecules. So what microwave ovens heat is not the whole food, but just the water part of it. So it can only heat water, none of the other substances. And that's why you can only heat objects that have some water content. Otherwise, things will not be heated by cannot be heated by microwave ovens. However, you do need, in order to have effective cooking, you need large number of photons because single photon energy is quite small. So we'll talk about other properties of photons in the next video.